Hello again. Let's, in part two of this Unit 4.2 lecture, do number 2 here. So it's another Laplace transform integral, only now we're going to bring in integration by parts here. So this is going to be an interesting example, so please pay attention. And go ahead and try it first if you like, but we're going to find the Laplace transform of the variable t, right? So seemingly innocuous function here. So by definition, this is the integral from 0 to infinity, e to the minus st times t dt, right? By definition, this is the limit n goes to infinity, integral 0 to n, e to the minus st times t dt. All right, so let's use integration by parts. We have a hint here as to the choice for u and dv. So let's go ahead and follow that. So if u is t and du is then dt, dv is going to be e to the minus st dt. And v, remember we're integrating, or we're going to find the antiderivative with respect to t. So it's going to be e to the minus st over negative s. Okay. All right. So what we're going to get here, and this is going to look a little bit different from what we did in Calc 2, but since we're all math majors, let's challenge ourselves here. So instead of like first finding the antiderivative without the limits of integration, let's actually keep them, and then here's how it looks when you do integration by parts. So we're going to have this limit here. That's not going anywhere, at least not yet. Now we're going to have big parentheses, and now the uv goes here, so we get u times v, well that's t e to the minus st over negative s, and now 0 to n will be here, and now minus the integral of 0 to n v du. So we get, let's see, e to the minus st over negative s dt, right? So that's v du. All right, well this is the limit n goes to infinity. You'll notice here, well, let's see, we're going to have plug in n, so we get n times e to the minus sn over minus s minus, and then, well, 0 is right here. 0 gets plugged in for t, and so everything else then is 0, right? And now here I actually get a double negative, and so that's actually plus integral 0 to n e to the minus st over s dt, which is the limit n goes to infinity, n e to the minus sn over minus s. And now we're going to take the antiderivative again. So what we're going to get is plus, we get e to the minus st over, well, we already have an s down there, and we're going to throw another factor of negative s down there, so you get minus s squared. Okay. And so this is the limit n goes to infinity, n e to the minus sn over minus s plus, well, plug in n, so you get e to the minus sn over minus s squared, minus, plug in 0, you get e to the 0 over minus s squared. Okay, so you'll notice here this is just plus 1 over s squared here. So I'm going to actually move that out of the limit because it has nothing to do with the variable n, right? And that's where we're taking the limit with. So we get limit n goes to infinity, n e to the minus sn over minus s minus e to the minus sn over s squared. Just moving the negative. The plus minus is just minus. And now this is plus 1 over s squared. Okay, so let's see what happens as n becomes large. So here, I think this is the easier one to see. we see that once again n is large and positive because n is going to infinity. So that means that in order for this limit here to be finite, we want this limit to exist. And our only choice is for it to actually go to 0. And so s has to be positive, right? So now, if s is positive, then this goes to 0. So this goes to 0 if s is greater than 0. Notice s cannot be equal to 0 because we're dividing by s. What you get is this going to infinity, but this going to 0, right? So n goes to infinity, it's right there. But e to the minus sn, because s is positive, goes to 0. And so what you actually have is a 0 times infinity indeterminate form here. But because e to the minus Sn is going to 0, that actually will kill off everything faster than n going to infinity will blow up. So in fact, this also goes to 0 if s is greater than 0. So I encourage you to review this from Calc 2. We had a couple of these problems, I think, when we talked about improper integrals. So I think that was probably chapter 6 of Calc 2. So please review that. But we saw something like this where you had a polynomial factor, which in this case n, multiplying a exponential factor that was going to 0. And so the exponential factor is going to win that fight. And so because the exponential factor is going to 0, n times that is also going to 0. Okay, so what we get is just 1 over s squared. And so our answer is L of t equals, well, it's just 1 over s squared, and now our condition is that s has to be positive, right? So once again, it was incumbent on us to find the condition that makes the Laplace transform exist, and in this case, it's just s being positive. All right, so now let's talk about linearity. It's a topic I brought up in the Unit 4-1 video, but essentially, I was able to split up you'll notice that I was able to split up a Laplace transform, think way back when, at like a plus sign, and then I was able to factor out a constant. And so you see we're doing the same thing here. So let me actually show you how this works. So let's suppose we wanted to take the Laplace transform of 2t plus 1. Well, by definition, we get e to the minus st 2t plus 1 dt, and we integrate that from 0 to infinity. That's the definition of Laplace transform. Now, if I simplify within the integral, I get the following: e to the minus st times 2t plus e to the minus st times 1, right? And now all of that is dt. Well, what we know about integrals is that they are linear, meaning you can split up an integral at a plus sign. That's how we do all of our antiderivatives. If there's a plus, you can just split it up there. Same goes for a minus. So in fact, this is the integral 0 to infinity e to the minus st times 2t dt plus the integral 0 to infinity e to the minus st times 1 dt. Okay? And now what we know further about integrals is that multiplicative constants factor out. This is also a property called linearity. It's addition, subtraction, and constant multiplication. You can sort of separate in this fashion. Okay, well, what is this here? And what is this here? Well, this is 2 times, this looks to me like the definition of the Laplace transform of t, right? And this here looks like the definition of the Laplace transform of 1. And so, ta-da, we have shown that the Laplace transform of quantity 2t plus 1 is twice the Laplace transform of t plus the Laplace transform of 1. And so the big remark here is that linearity of the Laplace transform is inherited from linearity of the integral. So whether or not you knew that this property of integrals, that you can split them up at plus signs and factor out multiplicative constants, whether or not you knew that was called linearity, now you know. And this is why the Laplace transform, because it really is just an integral. That's why the Laplace transform is therefore also a linear operation. Okay, in the next video we'll cover page 3 of the notes, and I think that'll be the last page of the notes for Unit 4-2.